So if you remember for hypothesis testing, there's two different type of hypothesis testing: is the null hypothesis and the alternate hypothesis. So the null hypothesis is the default position. It is saying like what we think it was, we're still gonna think is that value. And the alternate hypothesis is what they're trying to claim it is. So we're going to continue on with that. So I'm going to go over to my notes. So on the notes, I'm on chapter 8, page 6. So let me put that on the board. So chapter 8, page 6. All right, so that's chapter 8, page 6. So pretty much we're going to finish up this one page, and that's it for 8.1, and then we're going to get into 8.2. All right, so one thing you should kind of know, so at the end, once we finish our hypothesis test, what we want to do, we want to come up with a conclusion. The conclusion, you got to state, what can we conclude about the alternative hypothesis? So for this, you remember, we're never going to make a conclusion about the null hypothesis, because the null hypothesis is already assumed to be true. So we never make a statement about the null hypothesis. We're always trying to make a statement about the alternative hypothesis. So let me see. So we're always trying to make a statement about the alternative hypothesis. So whenever we're making a conclusion, you never want to put we accept the null hypothesis. We're pretty much all you're going to state is there enough evidence or is there not enough evidence for the alternative hypothesis. Because if you kind of think about it, like in the court system, they never say anybody is innocent. They pretty much just say you're guilty or you're not guilty, but they never truly say you're innocent. They're saying there either is enough evidence to prove something or there's not enough evidence to prove something. So just like that, pretty much we're going to make conclusions for this next problem. So for this one, says according to a study published in March 2016, the mean mile per gallon for the hybrid car is 50. And it says a researcher believed that the mean mile per gallon has increased since then. So if you kind of remember on last week when we did the null hypothesis and we did the alternative hypothesis, and we did this last week, we said the mean is equal to 50, and we said mean is greater than 50. If you're wondering how we got that, you go to last week notes, and there should be some notes about that. All right, so if you look at part A, it says, suppose the sample evidence indicates that the null hypothesis should be rejected. So for this one, telling us we should reject the null hypothesis. So they're telling us the null hypothesis is incorrect, and the correct one is the alternate hypothesis. So the way that we'll state this is as follows. So we'll say there. So since we're trying to prove the alternate hypothesis is correct, if we reject the null hypothesis, that's saying that the alternate hypothesis is correct. So that's stating there is enough evidence. So we're going to say there is enough evidence to support the alternative hypothesis. So you want to put there is enough evidence to support the alternative hypothesis, but normally you don't want to put the alternative hypothesis. You usually want to state what the alternative hypothesis is. So we're going to put there is enough evidence to support the alternative hypothesis that the mean mile per gallon for a hybrid car is greater than 50. And that'll be it. So that'll how you will state the term, well, state your conclusion if we reject the null hypothesis. So if we reject the null hypothesis, we'll state there is enough evidence to support the alternative hypothesis that the mean mile per gallon for a hybrid car is greater than 50. And that's A. Any question in regard to A? All right, so let's do B. So if you look at B, it says, suppose the sample evidence indicate the null hypothesis should not be rejected. So in this case, we're stating that we're not rejecting the null hypothesis, that actually the null hypothesis is correct. So since we're stating that the null hypothesis is correct, so in this case, since they're stating the null hypothesis is correct, remember, we're never going to put that the null hypothesis is correct. For this one, we're going to say there is so we say there is not enough evidence to support the alternative hypothesis that the mean mile per gallon for a hybrid car is greater than 50. So if you kind of look at both the alternative hypotheses, well, if you look at both of the conclusions, pretty much both conclusions should be relatively the same. The only thing different is whether you put there is enough evidence or there's not enough evidence. So anytime I reject the null hypothesis, you're always going to say there is enough evidence. Anytime you fail to reject the null hypothesis, that's when you can put there's not enough evidence. But that's it for B. Any question for B? Wait. All right, so let's go on to 8.2. So in 8.2, this is where we're going to start doing hypothesis testing. So this is where we're going to start doing it. Pretty much, we're going to do the whole pretty much portion of it. So we're going to start with coming up with a non-alternative hypothesis. Once we come up with the non-alternative hypothesis, we're going to test that non-alternative hypothesis to test to see if we should reject or fail to reject the null hypothesis. Once we figure out if we should fail to reject or once we figure out to fail or to reject the null hypothesis, we're going to come up with a conclusion. So this is what we're going to work on for 8.2. And for 8.2, we're going to be working on proportional data set. So let's get started. All right. So right here, it's just me restating the central limit theorem. So for the central limit theorem, it says if we do n times p times q, then that should be greater than or equal to, well, sorry. If I do n times p, that should be greater than or equal to 5. And if I do n times 1 minus p, that should be greater than or equal to 5. So this is just restating the central limit theorem condition. All right. So let's go on down. All right, so up next, this is the formula where we're gonna use, but for this one, we're actually gonna let the calculator do all the work for us. So for this one, don't really worry about this formula. We're gonna let the calculator do that work for us. So first thing we're gonna work on is the null alternative hypothesis. You should be already kind of used to this. So if you look at it, we have P, which P is the population proportion. And then you have PO, where that's where you're going to put the claim. So whatever they're claiming, that's where we're going to put on P naught. So for P naught, we're going to put whatever they're claiming. For P, that just represents the population proportion. So say if we're doing, say if we want to test to see if a coin is fair. If the coin is fair, we're going to say P naught is 0.50. So you will put HO, P is equal to 0.50. So you just know P naught, which is this, is equal to whatever they're claiming. So they're claiming is 50%, you put is 50%. They're claiming is 20%, you put 20%. Any question in regard to the known alternative hypothesis? So let's scroll on down. All right, so we'll skip this. All right, so let's go right here. So for this one, we're gonna go over how do I know if I should reject the null hypothesis or if I should fail to reject the null hypothesis. So to figure out if I should fail or if I should reject the null hypothesis, we're gonna use this rule of thumb. So for this one, if you look at it, if p-value is smaller than or equal to alpha, we're gonna reject the null hypothesis. If p-value is bigger than alpha, then you fail to reject the null hypothesis. And I'll show you a little bit how to find p-value, but for right now, it's kind of go with me that if p-value is less than or equal to alpha, we're going to reject the null hypothesis. If p-value is greater than alpha, then you're going to just fail to reject the null hypothesis. And this will always be the case. So all you have to know is get your alpha compared to p-value, and whichever one is bigger, that's going to tell me if I should either reject the null hypothesis or if I should fail to reject the null hypothesis. Any questions so far on when to reject the null hypothesis or when to fail to reject the null hypothesis? Yeah, all right. So let's do some of these basic ones. So if you look at this problem, we have p-value is equal to 0.27. We have alpha is equal to 0.10. So we're going to compare them versus each other. So we say p-value of 0.27. We're going to say alpha of 0.10. All right, which one is bigger, alpha or p-value? So if p-value is bigger, put A on the chat. If alpha is bigger, put B. All right, so it looks like I got 2 A's and 2 B's. All right, guys, so this is something I can't really help out with. You have to just know, like, if you look at 0.27, 0.27 is bigger than 0.10. So for this one, you want to say p-value is bigger than alpha. So if I go back and if I look at these two, you want to look at where is the case where p-value is bigger than alpha. So if you actually look for that, that's the second case. So in the second case, you have p-value greater than alpha. So since that's the second case, you say fail to reject HL. And that would be it for that first example. Any question for that first example? That's the null hypothesis. No. Yeah, HO is the null hypothesis. All right, so let's try doing the second one. So we have p-value, which is 0.001. We have alpha, which is 0.01. So let's say this is A. Oops. This is B. So let's go ahead and try to figure out which one's bigger. So which one's bigger, the p-value, which I denoted as A, or alpha, which I said was B? All right, sweet. So we get B. All right, so since B is bigger, thank you, Aaron, you want to say reject the null hypothesis. Okay, if you look right here, when p-value is smaller than alpha, you kind of want to go ahead and reject the null hypothesis. And that's it for the second one. All right. Any question on when do we reject or when do we fail to reject the null hypothesis? All right. And you kind of remember when we reject the null hypothesis? No. Yeah, they're never going to be the case where they're the same. Yeah, like it's never going to be likely that they're the same. There should always be different. So in our case scenario, they should always be different. All right. So let's go ahead and do a problem. So for this one said cell phone. A researcher obtained a random sample of 1,000 people and find that 534 are in favor of the banning cell phone use while driving. Does this suggest that more than 50% of people favor the policy at a significant level of 5%? All right. So first thing we're gonna go ahead and do, we're gonna go ahead and just label everything. So let's go ahead and label everything. So we're gonna label N, we're gonna label X, we're gonna label P, well, P not. We're also gonna go ahead and label alpha. All right, so we're gonna go ahead and label N, X, alpha, and P naught. So let's go ahead and let's first label what N is. What's my sample size? How big of a sample size do we have? Oh, thanks, Brianna. So we have 1,000. All right, of those 1,000, how many of them are in favor of banning cell phone use while driving? Oh, 534, perfect. All right, so for this one, what is my significant label, otherwise known as alpha or a type 1 error? So what's my significant level? Yeah, 0.05. All right. And what are they claiming should be the percentage of people who favor this policy? Yeah, 0.50. All right. Everybody good with that so far? All right, so first thing we're gonna go ahead and do is we're gonna look at the first thing. So here's the first one. So it says check to see if the data is approximately normally distributed. So for this one, they just wanted to use the central limit theorem because if you look at the original problem does not state that our distribution is a normal distribution. So they're not telling us it's a normal distribution, but what we want to do, we want to see if this is approximately normally distributed. To check to see if it's approximately normally distributed, we're going to check this condition that n times the proportion of the claim has to be greater than or equal to 5, and n times 1 minus the proportion of the claim that has to be greater than or equal to, well, not 10, but 5. So I'm going to go ahead and check that condition for both of them, and I want to see if both of those conditions pass. All right. So if you look at it, all I'm going to do right now is plug in. All right. So if I do 1,000 multiplied by 0.50, you get 500. So if you get 500, 500 is greater than 5. So that checks out. So then what you want to go ahead and do is check another condition, which is this condition over here. So we have to do 1,000 times 1 minus 0.50, which again will give us 500, which is bigger than 5. So that one also check out. So since both of the conditions check out, we're going to say, here, let's do it in a different color. We'll say the data is normally distributed. And that'll be it. Any question on how do we check to see if it's approximately normally distributed? All right. So let's do the second part. So the second part, if you look at it, it says state the null and the alternate hypothesis. So to state the null and the alternate hypothesis, that is saying we want HO and we want H1. So if you look at this one, we're going to say P is equal to the claim of the proportion they're claiming at 50%. So you say P is equal to 0.50. This one will also be P and 0.50. But what are they trying to prove? Are they trying to prove that it's more than 50%, less than 50%, or just not equal to 50%?
More.
Yeah, more. So since we're trying to prove that it's more than 50%, you put greater than. Any questions so far how I got more than? All right. So up next, we're going to do the test statistic. So this is where you're going to let your calculator do most of the work. So for the test statistic, you're going to need an X value, which is 534. You're going to need N, which is 1,000. And you're going to need P naught, which is 0.50. All right, so I'm first going to show you how to do this in Class Calc. Once we do it in Class Calc, we're also going to do this on the TI-84, but I'm first going to show you how to do this in Class Calc. So when we're doing the test statistic, we want one thing. The test statistic, in this case scenario, is going to be we want to find what the Z value is. Because the Z value is going to tell us how far away from the average it is. So it's going to tell us how far away from 0.50 are we. So kind of remember, the further we are from 0.50, the bigger the gap we have. The closer we have, or the closer we are to 0, then the less gap do we have. So if we want to see if there's a difference, we should get a high Z value. If there's no difference, we should get a Z value that's close to 0. All right, so right now I'm gonna go ahead and transition over to Class Calc. All right, so in Class Calc, you wanna make sure that you're in, what is that mode? Be sure you're in graphing mode. Then you wanna go here where it says stats. You wanna go here where it says tests. All right. Any questions so far on stats and tests? Okay, so since this is a proportional hypothesis test, if you look right here where it says one prop Z test, you want to click right here. So we click on one prop Z test. And if you look at it, it's asking for 3 things. It's asking for the null, well, for PO, it's asking for X, and it's asking for N. So for P naught, you put 0.50. For X, you put 534. And for N, you put 1,000. All right. If you look right here, it gives me a Z value of 2.15. Any question? I got the Z value of 2.15. All right, so let's look at the Z value. Is the Z value close to 0 or is it pretty far away from 0? So you're saying me 2? Well, if you kind of remember back when we're like back at chapter 3 or chapter 4, I forget which one, most likely chapter 3. If you remember for chapter 3, we said if we get a Z value more than 2 standard deviation away from the average, that's far away. So we're kind of using that same logic here because you want to look at this Z value and you have to go like, how far away are we? If you're more than 2 standard deviation away, that's pretty far away. So that's our Z statistic or our test statistic. Our test statistic is telling you how far away are you from the claim. So since we're pretty far away from the claim, they're kind of telling us there's a big difference between what we're claiming and what our sample is saying. So kind of telling us our sample is not backing up what our claim is. So they're kind of telling us we have a big difference between the two. Okay, so everybody get how we got that test statistic of 2.15? All right, so up next I'm gonna go back to the notes, and what we're gonna do, we're gonna calculate the p-value. All right, so that's my test statistic. So you put test statistic at 2.15. Over here for p-value, now we're gonna get what is the likelihood of this event occurring. So you have to look back at your test statistic, and you have to look at that z-value and see like how likely is that event of occurring. So when you're looking at the p-value for Class Calc, what you have to remember what your alternate hypothesis is. So my alternate hypothesis, we got it to be this. So my alternate hypothesis, we said P is greater than 0.50, correct? So when we look at Class Calc, we want to use the probability that has this symbol. So we want to use the probability that has this symbol. Because once I go back to Class Calc, you're going to notice there's 3 different probabilities, but only one of those probability is correct. So if you look at Class Calc, if you look at it, it has the less than symbol, it has the greater than symbol, and it has the not equal to symbol. So in our case scenario, since our alternate hypothesis is greater than, we want to use this symbol right here that says 0.0157. So this is our p-value. So we get p value is equal to 0.0158. Any question while we're using the p-value that says 0.01576? All right, so that's how you get the test statistic, and that's how you get the p-value on ClassCalc. I'm now going to show you how to get the p-value and the test statistic on the TI-83 or 84. So if you have the TI-83, 84, make sure you have it out. So first you want to go right here where it says stats. So here. So first you hit the stats button. Then what you want to do, you want to move it over all the way to the end where it says test. So we go here where it says test. And you want to make sure that you choose the, if you look at number 5, you want to choose the number 5 that says 1 prop z-test. The prop just means proportional z-test. So I'm going to do number 5. So if you look at it, it's saying P naught. P naught we said was 0.50. X was equal to 534. N was equal to 1,000. And then if you look at your calculator is a little bit different because in your calculator, it wants you to tell it what the alternate hypothesis is. So in our case, since alternate hypothesis we say is greater, you want to choose this very last symbol right here to say is greater. And then you go over here, calculate, you go to calculate. If you look at it, you get the same z value. It says z is equal to 2.15034. If you look at the p, which is your p value, you get 0.01576. And that's your answer for the p value. So for ClassCalc or the TI-84, both of you should be getting this, roughly the same answer. Any question for the TI-84? All right. So let's go back to the notes. All right. So if you look at where it says p-value and interpretation, so the interpretation, just tell me if I should reject the null hypothesis or if I should fail to reject the null hypothesis. So if you kind of remember when we, in the last section, in order for us to decide if we should reject the null hypothesis or if we should reject the null hypothesis, what you want to do, you want to use the alternate hypothesis. So, well, sorry, you want to use your alpha. So if you go back to the beginning, you're going to see that we chose alpha to be 0.05. So since alpha is 0.05, you put that here. So which one is bigger, p-value, which I'm going to label as A, or alpha, which I'm going to label as B? Cool. One person out there listening. 2. Yeah, so if you look at it, B is actually bigger than A. Okay, if you look at 0.05, 0.05 is bigger than 0.015A. So since alpha is bigger than p-value, in this case, we're going to come up with the conclusion that we should reject HL. Any question why we reject the null hypothesis?
Can you repeat that one more time?
Repeat what?
You said the reason why it's rejected is because the p-value Is
So
smaller?
yeah, the reason why you reject the null hypothesis is because p-value is smaller than alpha. If it would have been vice versa, where p-value is actually bigger than alpha, in that case, you would have said you failed to reject the null hypothesis.
Okay.
But yeah,
It's because I missed last class and I haven't been able to watch it, and I joined late right now because I had a doctor's appointment. So I'm looking at my notes. So I'm trying to like make sense of it in my brain. Okay.
yeah, if it's something you're just jumping into, it probably doesn't make sense right now. But you give it some time. But yeah, so for this one, since p-value is smaller than alpha, you just say reject the null hypothesis. Yeah. All right. Any question in regard to reject the null hypothesis?
I'm confused. Why is there a p on the left and then there's a p-value? Like the p is 0.50 and then the p-value is 0.0158.
Well, this is telling you the probability occur. So p-value is just what we found. This is the population proportion. Yeah, so the p-value is what we found because the p-value is telling you how likely is this event is of occurring. But the population proportion, or the p, is those two are not the same. So p and p-value are not the same. P is the population proportion. P-value is what we found using the TI-84, the class calc, but p-value is giving us the actual probability of us getting this outcome, given that the null hypothesis is true. But you kind of just know that these two are different from each other.
Okay.
All right, so last thing we're gonna go ahead and do, we're gonna go ahead and just state a conclusion. So the conclusion, remember, we're always gonna make it about the alternate hypothesis. And in this case, if you look at it, we reject HO. So if I reject HO, so going back up here, that means I'm saying this is not true. So if I'm saying the null hypothesis is not true, that means we're stating that the alternate hypothesis is true. So we're going to state something like that. So we're going to say, there is enough evidence to support the alternative hypothesis that so we just state for the conclusion, we'll state there is enough evidence to support the alternate hypothesis, and then you just want to state what the alternate hypothesis is. So in this case, the alternate hypothesis is that the proportion of people who support the policy is greater than 50%. And just remember, the policy is that cell phone use while driving should be banned. So that's the policy that they're supporting. So they're saying a majority of the population is in support of this policy. And that's it for that first problem. Any question for that first problem for our hypothesis testing? All right, so I'll give you a minute in case you're writing something down. And then we'll move on to the second one. All right, so let's move on down. Let's see. Here, so let's do this problem. So we're gonna skip that problem that was next. We'll come back to it once we're done with this one. But let's work on this problem. So for this one, it says in 1997, 46% of Americans said they did not trust the media when it's come to reporting the news fully, accurately, and fairly. In a 2017 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At the alpha equal to 0.05 level of significant, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? All right, so the first thing what you want to go ahead and do, just go ahead and just label everything. So we want to label what N is, we want to label what X is, and we want to label P naught. All right. So for this one, what's my N?
1010.
Yeah, 1010 or 1010. Perfect. All right. How many people don't trust the media?
46%.
Well, I want how many people, not the percentage.
525.
Yeah, 525. All right. What was the last percentage of people who did not trust the media?
0.46.
Yeah, 0.46. Also for this one, do they give me an alpha?
0.05.
Yes.
Yeah, 0.05. All right, so for this one, we get N is equal to 1010. We get X is equal to 525. We get P naught is equal to 0.46. And lastly, we get alpha is equal to 0.05. Everybody good so far with those four things noted?
Yes.
All right. So let's do the null and let's do the alternate hypothesis. So the null hypothesis should probably be the easiest thing. Let's see. Let's take a look. So the null hypothesis, you're gonna say P is equal to P naught. But since we already say P naught is equal to 0.46, you put 0.46 here. So you get HO, the null hypothesis P is equal to 0.46. So the null hypothesis is just stating we still believe that 46% of Americans don't trust the media when it comes to reporting the news. So that's what the null hypothesis is saying. It's saying that percentage is still relevant today. So for our alternate hypothesis, we want to say, okay, do they think that that number is less than 46%? Is it bigger than 46%? Or is it just not equal to 46%? So what are they trying to prove?
Bigger.
Yeah. So if you look at it, it says, oops. If you look at it, it says increase, which means bigger, which means greater than. All right. Everybody get how we got the null and alternate hypothesis? All right. So up next, we're going to, and we're going to do a test statistic. So if we're using ClassCalc or if you're using the TI-84, you go to your relative test and just run it. So I'm going to show you how to do it with ClassCalc. So in ClassCalc, let me go ahead and share my screen. So what I'm gonna do, I'm just gonna erase all of this and just re-enter the information. So we'll do 0.46. We'll do X. X is 525. And you enter N, which is 1010. Cool, good job. So you should have gotten the test statistic is Z is equal to 3.81. And for this one, which p-value would I use? 0.9999, 0.000068, or 0.000137113? Which of these three p-values should I use? Yeah, you want to use this one over here, the one that says 0.000068. So that's what I'm gonna put for p-value. So I'm gonna say p-value is equal to 0.00006, and we put 9, because technically I just rounded to 0.6 now. All right. So that's your z value, and that's your p value. So z value is 3.81, p value is 0.000068. Right. Any questions so far on how I get the z value or the p value from the calculator? All right, so of that, I'm going to go ahead and show you how to do this on the TI-84, in case you have a TI-84. So the TI-84, once again, you hit the stats button. You go to, you go over here where it says test, and you do a one prop Z test. All right, so if you look at this one, I have to change it to 0.46. Oops, enter something wrong. Oh, put a comma. 0.46. My X is 525. And this one is 1010. And then make sure that you put greater than, and you go to calculate. So if you do use the TI-84, you do have to be careful, because if you look right here, they put p value is equal to 6.8586. But if you notice all the way in the end, it says e to the negative 5. So the e to the negative 5, you're telling me I get this decimal place and I move it 5 places over to the left. So if you move 5 places over to the left, you should get 0.000068. Right. And that's it for the TI-84. Any question for the TI-84? Okay, so let's go back to my notes where we could finish off this problem. All right, so we have p-value, which is 0.00069. We have alpha. Alpha we said was 0.05. Which one's bigger, alpha or p-value? Yeah, so alpha is bigger. So if alpha is bigger, you're gonna reject HO. Everybody get why we reject the null hypothesis? All right, so if you kind of go back to the null and alternate hypothesis, remember, we're rejecting this. So since we're rejecting the null hypothesis, we're concluding the alternate hypothesis is correct. So we're concluding that the percentage of Americans who don't trust the media is actually greater than 46%. Because that's what our data set or our sample is telling us. It's telling us, no, we shouldn't think that it's still 46%. It's actually more than 46%. So that's where we're going to state in our alternate hypothesis. So for this one, we'll say there is enough, oops, evidence. And that would be it for that one. Any question in regard to the last problem? All right. Any question in regard to this last conclusion? Okay. So we're gonna go back to the one that we skipped, and we're gonna do this problem. All right. So this problem is actually a real problem. Give me a minute. The thing just stopped sharing. All right. So this next problem is actually a real problem. So for this one, what I want you to do, read the problem. And what I want you to do, I want you to think about what type of alpha value should we use for this one. Because for this one, I'm leaving the alpha up to you. So you kind of know for alpha, the bigger the alpha, that's telling you the less evidence you want. The smaller the alpha, so the closer it is to 0, that's telling us the more evidence do you want. So say if we use alpha of 0.01 compared to alpha of 0.20, the alpha of 0.20 telling us we don't want that much evidence, but the alpha of 0.01 is telling you that you want a lot of evidence. So read this problem and try to decide what alpha level should you use. So I'll give you 3 options. You could use alpha of 0.01, you could use alpha of 0.05, or alpha of 0.10. So look at the case scenario and try to decide which one will be best for this one. All right, so there's now 0.5. All right, so let's read out this prompt. So it says Christine Gilbert was a nurse at the Veteran Administration Hospital in Northampton, Massachusetts. She had a reputation of being particularly good in crisis. If a person went into cardiac arrest, she was often the first to notice something was wrong. Signal code blue and administer epinephrine. Often the patient's life was saved. Other nurses became suspicious both because of the number of cardiac arrests when Gilbert was on duty and also the number of deaths. Is there convincing evidence that the proportion of shifts with a death for shifts when Gilbert was working is greater than the overall proportion of 0.05? Well, 0.045, what alpha should be used? So for this one, we're talking about a problem where they suspect this person of killing these patients. So for this one, since we're trying to figure out if this person is killing people or not killing people, do you want a lot of evidence or do you want like little evidence?
A lot.
All right, cool. So I heard a lot. So if I want a lot of evidence, which alpha should I use?
Intense.
Well, remember in the beginning, I tell you, if you want a lot of evidence, then you want a alpha which is small.
Oh,
If you don't want a lot of evidence, then you want an alpha that's kind of big. So which
oh,
alpha should I use?
0.01.
Yeah, so you kind of want to use 0.01. All right, so we found our alpha level. All right. So up next, we're going to go ahead and we're going to go ahead and figure out what is our N, what is our X, and lastly, what is going to be our P naught. All right. So what was the overall death in the hospital overall? Well, if you look at the overall proportion of death for the hospital, it was 0.045. All right. So up next, we're going to use a two-way table to extract the information that we need from the two-way table. So for this one, we want to prove that Kristen Gilbert, that she either killed these person or didn't kill these person. So which one should I use? Should I use the data set when she was around? Or should I use the data set when she was not around? So should I use the yellow data set or should I use the red data set?
Yellow.
Yeah, so you want to use yellow because we only want to focus on when she was actually around. Because since we're trying to say she is killing these people, we kind of just want to worry about when she was actually around. We don't really want to worry about when she's not around. So how many times was she present?
74.
Before.
Yeah, so she was present for 74 times when they went to cardiac arrest. Oh, you know what? Sorry. Misread this. All right. Let's do that again. Which one should I use? Should I use the red one when it says yes, she was present, or should I use the yellow one when it says no, she was not present?
Oh God, why would you do that? I already highlighted my page.
Oops, sorry.
We need extra credit.
For real.
Good.
So we're gonna use the red
Oh, I'm
one,
confused now.
right?
Well,
Was the red?
Yeah.
well, we wanted to use when Gilbert were present, because this one is how many deaths were in the shift. So it's telling us yes, somebody died during the shift, or no, somebody did not die during the shift. So if you look at it, we
Wait.
kind of wanted to use the red one.
Oh, okay.
So we used the red one. So how many shifts did they actually get from Kristen Gilbert? Well, they got 257 shifts that she worked on. Of those 257 shifts, how many times did somebody die during her shift?
Is that 40?
40, perfect, good.
Oh.
So the 257 just represent how many shifts they were able to record, and the 40 represent how many times somebody actually died during that shift.
Okay.
Everybody go for N, X, and P.
Wait, can you repeat that?
So the N represent how many times or how many shifts they were able to get for Kristen Gilbert. So they were able to see that she had 257 shifts. And then what we want to do, we want to figure out like, okay, how many times did somebody die during her shift? So we want to use the 40. Because that's me how many times somebody died during her shift. Everybody go 40 is X, N is 257, and P naught is 0.045. All right. So let's do our null hypothesis. And let's do our alternate hypothesis. So for the null hypothesis is stating that Kristen Gilbert number and the hospital number are relatively the same. So we're gonna say there is no difference. So we're gonna say the proportion of deaths during Kristen Gilbert shift is the same as the hospital. So that's what the null hypothesis is stating. So we're stating that the proportion of deaths overall in the hospital is the same as Kristen Gilbert. Everybody good with that so far? All right, so let's do H1. So H1 is stating the alternate hypothesis. So you put P and you put 0.045. But in this case scenario, what symbol should I put? Should I put greater than, should I put less than, or should I put not equal to? Okay, what am I trying to prove?
Greater than the overall hospital?
Yeah, okay, if you look right here, it says greater than the overall hospital. So we're gonna put greater than. All right, everybody good so far? I got P is equal to 0.045 and P is greater than 0.045. All right, so I think we're gonna go ahead and do the test statistic. So for this one, actually before we do the test statistic, I want to calculate what P hat is equal to. Good. So P hat is equal to X divided by N, which is 40 divided by 257. So if you do 40 divided by 257, what's 40 divided by 257?
.157?
Yeah,
No, 0.156.
156. Good. Right. So if you actually look at this number, you go like, okay, the proportion of people who die in the hospital is relatively 0.045. But if you look at how many people died during Kristen Gilbert's shift, is 0.156. So do you think that's a big difference, or do you go like they're pretty close to each other?
Close.
So you think 9% different is close?
Oh my god, you said standard deviation when it's 2, it's a lot.
Well, I didn't say standard deviation. I was saying, are these two numbers different from each other?
Man,
Yeah.
I don't know.
Yes.
Yeah, these two numbers should be pretty different from each other. But if they're not kind of different from each other, they should be relatively close to each other. They should be like 0.05, 0.06. But if you look at it, it says 9% different. That seems like a pretty big jump. So let's go ahead. We're actually going to do the test statistic now. So the test statistic should kind of back up our thing that it should be a big jump. So we're going to go ahead and do this in ClassCalc. So for ClassCalc, we go to Stats, we go to Tests, and we go one prop Z test. So we go 0.045. You go N, which is 257. And you go X. Oh, sorry. You go 40. And then you go 257. All right. So if you look at the Z value that we get a Z value of 8.56. So we get a Z of 8.56. Yeah. So if you look at it, telling us pretty much the hospital overall percentage of death during shift and Kristen Gilbert percentage of death during her shift, there's a huge gap in between. Because if you look at the Z value, we got a Z value of 8.55 or 8.56. So that's kind of telling us there's a huge gap between the two of them. So since there's a huge gap between the two of them, it's kind of telling us like Kristen Gilbert more likely did it than not did it, because the chances of that occurring just by random luck is very little. Because if you look at the p-value, what is the p-value for this one? Yeah, 0. So it's kind of telling you there's like no way this could happen just by random luck. So pretty much the data kind of telling us like, hey, like when she's around, they're more likely a chance that people are gonna die during her shift versus when anybody else is around. Because her percentage of death rate is 15, almost 16%, versus the hospital, which is just 4.5%. All right, but that's the information for ClassCalc. Any question how we got this for ClassCalc? All right, so let me go ahead and do the TI-84. So for the TI-84, you go to Stats, you go to Tests, you go to one prop Z test. So we change that to 0.045. We change that to X, which is 40. We change that to N, which is 257. And you still choose greater than, and you go to calculate. All right, so if you look at the TI-84, it'll give you Z equal to 8.556. And then if you look at the p-value, say 5.90, e to the negative 18, which it just means you put 17 0 in front. All right, but that's it in regard to this problem. Any question on the TI-83 or sorry, TI-84 or ClassCalc? Okay, so let me transition back to the notes. For that you can see what did I enter for the notes. All right, so if you look at what I entered for the notes for the test statistic, we put 8.56. And then for p-value, we enter 0. So if you remember for p-value, you compare this to alpha, which alpha we had decided we're going to use the alpha of 0.01. So which one's bigger, alpha or p-value?
P value.
How is 0 bigger than 0.01? You don't have to leave. All right, yeah. So if you look at it, you get alpha, which is 0.01, and then p-value, which is 0. Well, anything is bigger than 0. So you put 0.01, which is alpha, is bigger than 0. So since alpha is bigger than 0, what should I say? Should I reject the null hypothesis, or should I fail to reject the null hypothesis? Okay. So you put reject the null hypothesis. This is slow. Yeah, 0.01 is bigger. Okay, if you look at, we say p-value is 0. This is 0.01. I could have 0.00001, and that will still be bigger than 0. All right, so the state of conclusion. So for this one, we're going to state a very simple conclusion. So think about if you are a jury, would you say that Kristen Gilbert is guilty of killing these people, or would you say she's not guilty of killing these people? So we'll say, oops, I'm not erasing. So we'll say she is guilty of killing these people. Because pretty much what we're doing, we're rejecting the fact that the proportion of death during her shift is the same as the hospital. And we're concluding that the proportion of death during her shift is significantly bigger than the hospital proportion of death during the shift. So that's it for that one. Any question for that last one? Well, the z-value is telling us like how far away from the null hypothesis we are. So if you look at it, since it's telling us we're 8.56 away, it's pretty much telling you there's a big gap between the null hypothesis and our data set. So you're telling us how far away are we? So if you have a big z-value, that means you have a big difference between the two values. If you get a z-value close to 0, it's telling you have like a low difference. And usually like for it to be close to 0, it has to be like 1 standard deviation away or less. So that's it for that last problem. Any question for that last problem? All right, so we're done with this one. Here, let's see something. All right, so let's move on to 8.3. So for 8.3, we're going to still be doing hypothesis testing, but now we're going to be doing hypothesis testing for the mean. So it'll be exactly the same thing. The only thing different, instead of saying test the proportion, we're going to be testing the average or testing the mean. So for this one, it just means that the null alternative hypotheses are going to change slightly. So instead of putting P, we're going to be putting mu. So we're going to say mu is equal to whatever they're claiming. So mu na is their claim. So if you look at the null hypothesis, all of them are the same. It will always say mu is equal to the claim. So whatever the claim is, we're always going to say they're equal to each other. What's going to change is in our alternate hypothesis where we're either going to say is not equal to, less than, or greater than. Any question for the null and alternate hypothesis for the population mean? All right, so let's scroll all down. All right, so let's go ahead and do this problem. So this one said in 2016, the mean year of experience among a nursing staff was 14.3 years, with a standard deviation of 11.2 years. A nurse manager took a survey in 2007 of a random sample 35 nurses at the hospital and found a sample mean of 18.37. Do we have evidence that the mean year of experience among nursing staff at the hospital has increased since 2016? Use a significant level of 0.05. Okay, so for this one, you kind of want to be careful because they're going to give you pretty much the same information. So we're going to find mu, we're going to find sigma, we're going to find n, and we're also going to find sample mean. We're also going to find what alpha is equal to. So let's find the easy one. What's my sample size? So what was the sample that they took?
Is it 35?
Yeah, 35, thank you. So we got 35. And if you look at that, so let's highlight this entire sentence. So what other information do they give me in that sentence?
The sample mean?
Yeah, so if you look at it, they gave us the sample mean. So if you look at in that same sentence, they gave me the sample and the sample mean. So usually whenever they give you the sample, in that sentence, they will also give you the sample mean or the sample standard deviation, whatever it is. All right. So let's go ahead and look at the 14.3. So the 14.3, what do they tell me? What is the 14.3?
The mu? No.
Well, 14.3 is, if you look at it, it's the mean. So they're telling you it's 14.3 is the mean, but did they tell me how big of a sample size did they took?
I thought it was 35.
Well, 35 was for this 18.37. So they told us they took a sample of 35 and they got the sample mean of 18.37. But they also got this mean, and I'm trying to figure out where did this mean come from. Did you tell me this come from a sample?
The years of experience?
Yeah, so well, they told me in 2016, but they don't tell me how big of a sample size we had. So since they don't tell me how big of a sample size we have, we're gonna just assume this is the population mean. So we're gonna assume this is 14.3. And also we're gonna assume that standard deviation is a population standard deviation.
Okay.
So far, everybody go with that labeling? All right. Also, last thing they gave me is alpha. Alpha, they tell me is 0.05. All right, so let's do the null alternate hypothesis. So for the null hypothesis, we're going to just assume whatever the mean was before is still that value. So if you kind of look at it, they told us that the mean year experience that was before in 2016 was 14.3. So we're going to assume it's still 14.3. So we're going to say mu is equal to 14.3. And we'll put mu 14.3 here. Do they still believe it's 14.3? Yeah, so they actually think it's greater than 14.3 now. So we have to use a greater than sign. All right, everybody got mu is equal to 14.3 and mu is greater than 14.3 for my null, my alternate hypothesis. All right, so let's go on, and now we're gonna do the test statistics. So once again, we're gonna let the calculator do our work for us for the test statistic. So for our calculator, we're gonna just need this information here to enter it. So I'm gonna go over and transition over to ClassCalc. So let me erase this. So we're gonna go over here where it says stats. We're gonna go to test. So 8.2 was one prop z-test. For 8.3, it's just gonna be a z-test. So you go right here where it says z-test. So if you look at the z-test, it's asking us for the mu, which we say is 14.3. It's asking us for population standard deviation. Population standard deviation we said was 11.2. If you look at X bar was 18.37. And lastly, n was equal to 35. Any questions so far? How I got mu, sigma, X bar, or n? All right, so let's see what do we get for our z value. So for z, what does it tell us z is equal to?
2.15.
Yeah, 2.15. 2.15. So if you look at the 2.15, it's kind of telling us there's a big difference between pretty much what we thought it was and what our sample is telling us. Because if you look at our sample mean, the sample mean was 18.37. And if you look at the population mean was 14.3. So telling us that difference of approximately like 4 years, that's a pretty big difference. If you look at the p-value, what p-value does it give us? Yeah, so it give us 0.0158. Everybody go on z value and p value. Okay, so that's how you do in ClassCalc. Let me show you how to do it with the TI-84. So for the TI-84, you go to stats again, you go tests, and you go to z-test. So for z-test, make sure that you're on stats. On stats doesn't mean that you'll be giving it all the information. So if you look at mu will be 14.3. If you look at sigma, is 11.2. If you look at X bar, is 18.37. 0.37. If you look at n is 35. And actually, let me go back to sample me because I didn't enter that correctly. Should be 7. And then lastly, make sure that you put greater than and you go to calculate. Right. So if you look at it, give me a z value of 2.1149, which is exactly what we got with the ClassCalc. And they gave me p value, which is 0.0158. Any question for the TI-84? All right, so let me go back to the notes. All right, so if you look at the notes for the test statistic, I put 2.15. For the p-value, we put 0.0158. And if you look at my alpha we said was 0.05. So let me put 0.05. So which one's bigger, alpha or p-value? Yeah, so
Alpha.
if alpha is bigger, what should I say? Should I reject or should I self reject? So we reject the null hypothesis. Yeah, so you want to reject the null hypothesis because if alpha is bigger than p-value, that's telling you that this is significant. Let's see. So it's telling you there's significant evidence to kind of tell us that the difference between the sample mean and the population mean is a significant difference. All right. So for this one, should I say there is enough evidence or should I state there's not enough evidence? Cool. So say there is enough evidence to support. All right. And that's it for that problem. So you put there is enough evidence to support the claim and then put whatever the claim is, that the population mean years of experience for nurses is greater than 14.3 years. Any question for that last one? All right, so let's do this last one. Yep. So we're not gonna do this part. So for this one, it says the number of years it took a random sample of 33 former smoker to quit permanently is listed. We know that the population standard deviation is 1.5 year. Health agency claimed that the mean time it takes smoker to quit smoking permanently is 6 years. A researcher doesn't believe the claim of the health agency and think it's more than that. At an alpha of 5%, is there enough evidence to reject the health agency claim? All right. So first thing we're gonna go ahead and do, we're gonna go ahead and label everything. So we're gonna label N, we're gonna label X bar, we're gonna label sigma, we're gonna label alpha. I think that's it. All right, so what's my N? So how big of a sample size do I have?
33.
What about population standard deviation? What's my population standard deviation?
1.5.
Yeah, 1.5, perfect. What's my alpha? Well, that's 0.05. What are they claiming is the population mean time it takes somebody to quit smoking?
Is it 6?
Yeah, 6, perfect. All right, and for this one, do they give me sample mean? Yes, no, maybe?
I don't think so.
Yeah, so they don't give me sample mean directly, but I could use this sample in order to find sample mean. So I'm gonna show you how to do that with your calculator. All right. So from this, we'll get sample mean. All right. Everybody good with that so far? All right. So let's do the null hypothesis. And let's do the alternate hypothesis. So the null hypothesis, we're going to say we believe their claim. So we believe their claim that it take on average 6 years to quit smoking. So we're going to believe this program, and we're going to say they could help them quit smoking in 6 years. But the alternate hypothesis is going to state the opposite. It's going to state that we don't believe their claim. And what do we think about the year that take them to quit smoking? Do we think it's less than 6 years, more than 6 years, or do we think it's different from?
More.
Yeah, we think it's more. Yeah. So that's going to be our null, and that's going to be our alternate hypothesis. Any question for our null and alternate hypothesis? Okay, so I'm going to go ahead and do the test statistic. So we're first going to do the test statistic, and this time around, I'm going to do it for the TI-84. So for you who have TI-84, hopefully you have them out. All right, so for the TI-84, the first thing you want to do, you want to enter the 33 numbers. So you want to go to stats, you want to go to edit, and you want to go and enter the 33 numbers. So I have to get clear this before I do that. So right here for L1, I'm going to put 10.7. Yeah, let's do it. Okay. All right, so once you enter all of the data set into L1, what you want to do, you want to go here where it says stats. You want to go where it says tests. And you still want to do a z-test. But what's going to change instead of you selecting stats, which means you're giving them all of the stats, what you have to do, you have to go over now to data, because now you want the calculator to look at the data that you enter. So I'm going to put data. So if you look at it, it asks for mu. So mu is still going to be 6. My sigma is going to be 1.5. But for my list, I'm going to tell it to look at L1 because that's where I enter all the information. And then right here, what you want to do, you want to hit the greater than button. Well, I already have it selected. So you go greater and you go to calculate. All right. So if you look at what I get Z is equal to 1.93. If you look right below, you get p-value, where p-value is equal to 0.027. All right, so that's how you do with the TI-84. Any question for the TI-84? All right, so let me switch it over to class calc. All right, so for class calc, same thing. You go to stats, you go to tests, you go to z-test. If you look on the top, it says stats and it says data. So if you have the data, you want to select data. So now it asks for mu. So mu is 6. It's asking for sigma, which is 1.5. And now it's asking us for the data. Wherever it says L, that means it wants you to enter the data. So you have to do 10.7, comma, 3.2, comma, 12.6, comma, 9, comma, 8.7, comma. So if you enter all of the data set in, if you look at it, it gave me Z value. So Z is equal to 1.93. And it also gave me P value. P value is equal to 0.027. So same thing if you do it with a TI-84 or with ClassCalc. Any question on how to do this with ClassCalc? All right, so let's go to the notes. All right, so that's p-value. So you get p-value of 0.027, and we get alpha of 0.05. So which one's bigger, alpha or p-value? All right, well, alpha is bigger than p-value. Since alpha is bigger than p-value, you want to reject HO. And since you reject the null hypothesis, that means there is enough evidence. So you say there is enough evidence to support the claim that it takes more. All right. So that'll be your statement for this conclusion. So you say there is enough evidence to support the claim that it takes more than 6 years to quit smoking. And that'll be it for that conclusion. Any question for the last conclusion? Are you talking about the class count? So you hit stats and then you do z-test and then you enter this information? It might be that you enter the numbers wrong, or you might have a comma somewhere. Do they have like a, let's see. Do they have like a triangle? Yeah, because if it has a triangle and the exclamation mark, that means something is not right. So I'm guessing you might have put a comma and you didn't put the number that go after that comma, or you might just have to take away the comma. But you just want to look over it and just make sure that you enter it correctly, because yeah, that's what it probably is. Any other questions? All right, so that's pretty much it for today, guys. So just remember, there's a quiz due today at the end of today. So if you still haven't taken that quiz, do so as soon as possible, because it is due today at 11:59 p.m. So whenever you can, take the quiz as soon as possible. It has 5 questions, and it is covering confidence interval for for standard deviation. So you might want to have the chi-square table ready for that one. Any other questions? All right. I'll let you write it down. Yeah. All right, guys. So that's pretty much it for today. So that's it for today. If you do have any follow-up questions, just remember tomorrow we have lab from 3 to 4:05. So if you do have any other question, or if you get stuck on any of the homework, or if you want to go over any of the question in the quiz, you can pop up tomorrow during the laboratory and I could go over that with you. All right, any question before I close this meeting? Correct. I said you need the chi-square table for the quiz today. All right, so there's no question. I'm gonna stop